recording started. Okay, so plan for today is to cover external data structures and B plus trees. So I'm going to start with external data structures. All an external data structure is something that's stored on external secondary memory. So things like stacks, queues, abstract data types, things that you might use in Java or object-oriented programming languages, they'll be stored in RAM. Variables will be stored in memory, whereas external data structures are all stored on a hard drive or an SSD. And this has some benefits. By using external data structures, data can persist beyond program execution. Unlike variables, which you lose after the program stops running, external data structures will remain on the storage device. Data can grow to sizes larger than RAM, so you're not limited to however much space your memory is limited to. You're just limited to however big your SSD or hard drive is, which means you can store a lot more data. And finally, data can be accessed and modified by multiple programs simultaneously. So whether this is a game and you want to track some statistics at the same time, or there's loads of possible use cases where you might have multiple programs which are trying to read the same data or write to the same file. And by using external data structures, you can do this because by default, your operating system will only allow one program to access a certain group of memory cells at a time, whereas that limit's not there with external data structures. Cool. Okay. And this was in one of the lectures, so I thought it would just be worth covering. When you want to read or write from a hard disk, these are the steps it takes to follow. So this is the amount of time it kind of takes to read or write to perform that operation on hard drive. So you want to move the disk head to the correct track. So imagine that it's a disk like this, and it's made up of a bunch of tracks. You want to move the head to the correct track. For example, say it's on this one, and then you have to wait for this to spin around until it's at the data you want. So if this is our data, you have to wait for it to spin for this green area to be under our head, and then the data has to travel past the head. So it will, as soon as it's past the head, we know we've read the data. And so just something to keep in mind, as a result of this, if we're reading or writing consecutive blocks, if things are stored in a serial file like this, it's a lot easier to read than scattered data that's just all around the disk, because then we have to move the read-write head a lot. So one thing that B plus trees and B trees use is serial files. They use files, and these files are often stored serially, meaning, they're often stored sequentially, meaning data is very close to each other, it's contiguous, making it a lot faster to read and write data. Does that all make sense in terms of external data structures? And I'll move on to B trees. Okay, let me just... Cool, yeah? Right. So, before we go to B plus trees, I just want to talk about B trees, because this is what B plus trees are sort of derived off of. So B trees, a B tree is of order M, so it has an order, is a type of n-ary tree with some restrictions or properties. So by n-ary tree, I just mean binary is just a 2-ary tree. You might have a tertiary, I'm not sure about that, but a 3-ary tree. This is just a type of n-ary tree, so it can have any number of children, and that number of children will be represented by this n value here. And it has some restrictions or properties. And these are the restrictions. So every node has at most m children, so this is the maximum number of children per node. Every non-leaf node, so everything that's not at the bottom of the tree, so not these, but it will be these, except the root, so excluding the root as well, has at least m over 2 children. We'll look into what that looks like in a second. The root node, if it's not a leaf node, has at least 2 children. So it will always have at least 2 children, and then it might have more, it might not. But if it's a leaf node, then obviously that restriction can't apply because it's just the root node. There's no children. A non-leaf node with C children contains C-1 search key values, which act as separators or discriminators to guide searches down appropriate subtrees. All that means is our nodes look something like this. Imagine we had 2 values in our node. We have 3 children, and we have two discriminators, or two values in here. So we might have, say, A, B, and then this will go to 3 more children. And this is just C minus 1 for 3 equals C. Okay, all leaf nodes appear in the same level. Okay, so this is something quite interesting about B trees. All of our leaf nodes will always be the same distance from all of our leaf nodes will be the same distance from the root. You'll never have something like this. It will always be all of your leaf nodes are on the same exact level. Okay, and B trees are always height balanced. So as a result of all leaf nodes being the same level, B trees will obviously always be height balanced. You're never going to have some sort of unbalanced tree where it's something like a linked list. That won't happen due to the way we insert and the way we search and remove nodes. And finally, update and search is of log n. We'll see why that is as well as we traverse our trees. Okay, moving on to B plus trees, the main event. Okay, so before we begin, I just thought of an example that might help us sort of visualize what a B plus tree kind of does. So on a website, let's say you wanted to select a date. You might see something like this, and you want to click this button, and a pop-up will appear. And then it might ask you to click a year that you want to select a date in. So I might select 2022, for example. And then after selecting that, it might tell me to pick a month. So right now we're in 2022, and we want to pick a month in 2022. So let's say I pick August. After selecting a month, it might ask you to select a date. So now I've got 2022, August, and let's say we want to select the 8th of August. So what we've done here is we've sort of picked an initial root, and then from there we've picked something which has pathed into something else, where we pick something, which has pathed into something else, where we pick something. So B plus trees basically work like this. Instead of having every possible combination, so 6 years times 12 months times, let's say, 31 days, instead of having that's going to be in the thousands of options, we just have to take 3 steps, and we can reach our target date instead of brute forcing through all of these. And so B plus trees just let us do this. They let us split up a bunch of data into segments and split those segments into segments and those segments into segments, and we can group them together and sort of take a certain path down the B plus tree to reach a certain target value. So B plus trees, a few key terms, a data record. All a data record is some element of data that we want to manage by the B plus tree. So an example could be a student record with an ID number, a name, an email address. So that could be anything that just stores a group of data. That's all associated. A key value. So this is the value by which we identify the record. So in terms of a student record, you might use their ID number or maybe their full name to sort of identify that student. You can almost imagine this as like a primary key in the database. Discriminator. So this is the value that we use to decide which path to take down the tree. So if this was our node, our discriminators would be here. They'd be the values inside these sort of squares. And that's how we decide what child to visit. And then our disk address, that just refers to an offset from the start of the disk file to a particular block in the file. So on the disk we have a bunch of files. All of the files will have data like so. And we might say, okay, we want to look in file 2 at offset 3. And so we want to look from everything here onwards. So all a disk address does is it's a location on a disk. Opposed to a memory location where that's just a sort of register address, this is an actual disk address. And we can use that to read and write from external data structure, from external data devices. Okay, does that all make sense? If there's any questions, drop them in the chat, but I'll continue. Okay, we have 2 types of B plus trees. So, well, 2 main types that we need to sort of be aware of. Record embedded and index B plus trees. So record embedded B plus trees is where we store the data records inside the leaf nodes of the B plus tree. The actual... Oh, missing a space there. That's going to annoy me. Okay. The actual data records are stored in the tree. So if we delete the tree, we delete the data. Whereas in an index B plus tree, we only store key values and disk addresses. So imagine our student ID example. We'd only store the student IDs and disk addresses to where information about the student with that ID is stored on your hard drive or SSD, which file it's stored in. And so in this case, if we delete the tree, we don't actually delete the data because the tree is just a reference to the data. And we're going to see some cool things we can do with that. So do these two make sense, the difference between these two? Cool. Okay. So, yeah, we've covered this, but every leaf node is at the same level, just something to keep in mind. And every non-leaf node, excluding the root, has at least m over 2 children. All this thing means is seal. So, if you do something like math.seal, all that means is we divide it, and if it's something like 20.5, we always round it up to 21. Yeah. So that just results in an integer from a decimal. So, yeah. Okay, record embedded B plus trees. So they look something like this. We have our root node, and say we want to search for a value. Say we want to search for 27. What steps would we need to follow? Someone drop it in chat. So this is our root node, and we want to search for 27. I'll give you a few seconds. Less than 27, less than 30. So we go down the tree to the block, second from the right. Yeah, perfect. So we know that 27 is in between these two values. Oops. Is in between these two values, 27 and 30. So we go down to this node. And then finally, we know that we can search this node. Because it's a leaf node, we just have to search for the 27 data inside that node. So we look at 23, that's not 27. We look at 25, that's not 27. We look at 27, perfect, we found it. And so, since this is a record embedded B plus tree, our actual data for, say, student with ID 27 will be here, inside this node. So we can just pull that out and do what we want with it. What if we were looking for 28? What would we do then? So, we know that 28 is in between these two. So we'd go down to the same node as we did for the 27. But when we search this, we'd see if 23 is 28, no. 25, no. 27, no. And because we've reached the end of the node, we assume that that data isn't stored in the B plus tree. We wouldn't go here, because if 28 was here, then we would have ended up going down this memory address, but we didn't. Sorry, this disk address, but we didn't. So as soon as we get to a leaf node, the value we were searching for, it has to be in that node, otherwise it doesn't exist in the tree. We've not stored that data in the tree. Okay, cool. So, insertions. Insertions are a bit different. So say we wanted to insert the value 55. We have to do it in two parts. First, we have to search for where we would insert it, and then we insert it. So if you want to insert 55, we'd see that it's greater than 30, so it would go down this disk address here. We'd go to this node. And because there was an empty slot here, the 55 would go there. So this wasn't here before, but because there's an empty slot, we can just put the 55 there. And that's how we'd insert a value when there's an empty space. But if there's not an empty space, things can get slightly more confusing. So I'm actually going to trace through this. So say we want to insert the number 26. Does anyone want to talk me through how we might do that? Or drop some suggestions in chat. If you want to insert the number 26 into this tree, what would we need to do? is the... Oh yeah, sorry. So what this star means is that the data related to that key is stored there. So the discriminators don't have a star because it's just used as a value to decide what path to go down. Whereas the star just tells us that there's some value, some data associated with that inside the node. Yeah. Okay. So say you wanted to insert 26. We know that it goes in between these two. So we go down. But we're at a leaf node and there's no space to put the 26. So what we do in this case is we say, okay, 23, 25, 27. We want to insert 26. So 26 would go here. So this would be the resulting 4 nodes. If we could insert it here, these 4 nodes would be in here. And then we just want to order it so that it's 23, 25, 26, 27. Okay, so we have these 4. Now, what we want to do is we want to create a new node, a new leaf node, which looks something like that. 23 and 25 would stay in that left one, and we'd put 26 and 27 in here. So we'd distribute them between 2 nodes. 26 goes here, and 27 goes here. Okay, now we have 2 leaf nodes. We want to update these, so this arrow would actually point down here, and this arrow would go to this one, and this arrow would go to this one. So all we've done is we've created another leaf node, and we've split up the 4 that couldn't fit in one into 2 nodes of 2. Does that make sense to that point there? Okay, perfect. And then we've only got one disk address, so we can't point to both of them. So here we have to do something. We have to do the same, but up here. So we want to... Let me move this here. And this is what posting... This is where posting comes in, where we post this 26 upwards, because we need to create another one of these. So we want to bring the 26 up. So that means we'd have 10, 20, 26, 30. So now we have these 4 values. And so we split it again. These 2 will go in one node, and these 2 will go in another node. So 10, 20 would be there. Actually, let me do it like that. Okay. So we'd create 2 more nodes. 10, 20, and 26, 30. And then, instead of having this single node pointing to 3, these 2 nodes can now point to a lot more. So 10, everything less than 10 is this node here. Everything between 10 and 20, between 20 upwards is here. And then everything, well actually this one would go here. 26 and 30 would go here. And this can point to here. Okay, so it would look something like this. Is there a reason you picked 26 over 25? Oh, as in 25 was already in there. But, oh, are you saying if we decided to use this one to take up? To be fair, I feel like it might not make that much of a difference. But in all the examples I've seen, they've picked the first one of the second node as like the new key to post upwards. So, yeah. But I mean, you can try it out and see if it sort of leads you to the same complexity. Okay, so we have this, and we have this. I mean, this isn't a B plus tree. We've got 2 nodes. We can't have 2 root nodes. So then, all we do is we take that 26, and we just make another root node. And then this would point here, and this would point here. And this is our B plus tree. It's not the cleanest, but I've got a cleaner version of that here, where it looks something like this. Oh, one thing to keep in mind, when we're posting a reference upwards, we move it. We don't actually keep it here. So we'd get rid of that 26. That would just become 30. Wait, what did I... Yeah, so we'd get rid of that 26. This would just become 30. And then this can point here. This would point down here. And this would point down here. So we'd end up with something like this, which in turn looks like this. So the idea is we took this 26, we copied it up to here, and then we moved it up to here. And this is our new root node. And so the tree's increased in height by 1. Okay, so that's insertion. Deletion is very similar. The only thing is we do the reverse. So say we want to delete 5. All we'd do is we'd go down here and we'd see, okay, 5's in here. We want to get rid of it. And now we have an empty leaf node. So all we need to do then is get rid of that leaf node and get rid of the reference that was here, so that we have a single root node and this is just pointing to these 3. So whereas with insert we sort of work upwards, with delete we still work upwards, but we merge things together to sort of that which could lead to a reduction in the height of the tree, because it keeps it balanced at every stage. It could lead to, for example, the height. If we deleted 26 from this tree, it would result in this tree. That's insertions and deletions. So for a record embedded B plus tree at least. For an index B plus tree, there's 2 more subvariants of index B plus trees. So we have secondary B plus trees, where the records there might not be sorted in the data file, and so every entry in the leaf nodes just contains a key value and a disk address for each key value, for each piece of data. And a primary index B plus tree, where the records are kept sorted by the key value in the file, and so the leaf nodes only need to store discriminator values. They don't actually need to store locations, because the locations are derivable from the actual key value. So a primary index B plus tree, here's an example of that. So this record file at the bottom, let me pick a different color. This record file at the bottom is sorted. So 2, 3, 4, 5, 14, 16, 19, 22, 24, 29. So all this does is we have something like this. This is our root node. And then it's pointing to some leaf nodes. And these leaf nodes just represent data inside the record file. After inserting 4, that would lead to, because we can't fit 4 things in here, we'd have to create another node and then move this 24 there, and also move keep the 4 here, and then 17 and 24 would be in their own node. And then, but yeah, the idea is this record file is ordered, so that's why it's a primary index B plus tree. Whereas in a secondary index B plus tree, it's not ordered. So here, 17, 24, 4, 13. We have our root node, and this points to the leaf level, and then this points to the leaf nodes. One thing you might notice here is the leaf level is not equal to the record file. They're 2 separate things. In a primary tree, the leaf level and the record file, they were still 2 separate things, but no 2 discriminators, no 2 keys pointed to the same thing like this. Whereas in a secondary index, you might have multiple leaf levels pointing to the same block of text or block of data inside the record file. Yeah, okay. Is there any questions about anything there before I move on? If you go back to the insert 26, okay. Are you talking about this value? Okay, so what we do is, because at the stage where we're sort of bringing this 26 up, before we are at this stage, it would look something like this. We just got that 30 because before the root node was this, and we've just added the 26 in, and we've split it into 2 nodes. So we'd have something like this. And then all we do from there is we just repeat that post operation where we bring that 26 up. So we bring the 26 up, but the 30 stays here. And then that just points there, and that points there. Is it only the non-leaf nodes that need M over 2? Yeah, so the leaf nodes don't actually need seal M over 2. And the root node also doesn't need that. Yeah, I noticed that. I'm not too sure why these two are here. So because this is the leaf level, it can have a pointer which goes to the prev or the next leaf node. Because all the leaf levels are on the same height, they can point to each other, meaning we can traverse it sequentially like a linked list. So if we get to the bottom, say we want to search for 13 and search for the value after 13, we can just go here and then go here and see, okay, 24 is after 13. Whereas if we didn't have this pointer here, we'd have to search for 13 and then search for every number until we come to another one above 13. It just makes traversing the leaf level quite easier. Yeah. Okay, let's continue with bulk loading. Okay, so bulk loading, if we have a bunch of data, it makes sense to bulk load it into a new B plus tree instead of inserting it one by one, just due to complexity. Instead of having to search and then insert and then search, insert, search, insert, search, insert. Instead, we can sort all of the records and then we can bulk load it into a new B plus tree, which is a lot faster. So the idea is, we sort the records and then we construct leaf blocks. Whenever we add a new block, we insert into the parents of the leaf nodes. So we keep creating parents upwards. So let's say we have this list here. First thing we do is we sort it. So that just becomes that. So now we've got a sorted list. 1, 2, 3, 4, 5, 6, 7, 8, 9. And say we want to insert this into a B plus tree, and we want each node to have, of order 3. So each node has 3 discriminators. Okay. 1, 2, 3 would go into the leaf node. 4, 5, 6 would go into a leaf node. And because we just created a new leaf node, we have to create a parent. So we'd put a 4 here, we'd bring this 4 up, and we'd have something like this. One thing to note is these would all be data, so these would all have stars next to it. Okay, and then 7, 8, 9 would go into another leaf node. We'd put that there. And we'd have to update the parent. So we'd put a 7. We'd bring the 7 up here. Whoops. We'd bring the 7 up and we'd point to that. And there, we've constructed B plus tree by simply ordering it and then just putting that into the leaf values. Yep. Okay, so that's bulk loading in a nutshell. Complexity analysis. Okay, someone tell me what the complexity for these 3 operations are on a B plus tree. Okay. You're saying it's log n. That's correct. So log base m of n. Search is also log base m of n. Remove is log base m of n. If we imagine a binary tree, or let's imagine a binary search tree, where we have a value, and then a value, value. The reason this is log n, why is search log n in a binary search tree? So say we wanted to search for, let's put some example values in here. Say you wanted to search for 15, how many steps would it take? So if we wanted to search for 15, we'd look at, oh, what did I just click? Okay, we'd look at this 10, Yeah, good. 3. So we look at this 10 is greater than that. We look at this 14 greater than that. We look at this 15 equal. So it takes 3 steps. So log base 2 of there's 7 nodes here of 7, I believe, is 2 point something. So with a binary search tree, yeah, it's log 2 of not the height. N is the number of nodes in the tree. So log base 2 of n, where n is the number of nodes. So if we had something like 128 nodes, that would take 7 steps. Yeah, I think. Okay, yeah. So that would take 7 steps if you had 128 nodes to find any node. 2 to the power of h. Yeah, 2 to the power of h. I mean, that's assuming that the binary search tree is a maximal AVL tree that is perfectly sort of structured. If it was something like this, it wouldn't be 2 to the h. It would just be, yeah. So 2 to the h, assuming it's a maximal AVL tree of height h, with 2 to the power of n plus 1 minus 1 nodes. No, 2 to the power of h plus 1 minus 1 nodes. Yeah, okay. So yeah, a binary search tree takes log base 2 of n steps, because each node has 2 children and there's n nodes. So m here, when we're looking at B plus trees, m represents the number of children. Because if you think about it, if we have more children, there's more opportunity to what's the word? There's more opportunity to scope in on the solution or the target we're looking for on every step. And so you can almost imagine it as if we had something like 5 children. Every step we take, we're dividing the search space by 5. With a binary search on a sorted list, for example, 1, 2, 3, 4, 5, 6, 7, 8. Every time we look at something and compare it, we're dividing the search space by 2, and then dividing it by 2, and then dividing it by 2, and oh look, we found 6. But yeah, with a B plus tree, we're dividing it by a lot more. M in our case, because there's m children, and n is just the number of nodes in the B plus tree. So for insert, search, and remove, all of these will just be log base m of n, or a multiple of that, in terms of time complexity. I should probably make that bigger notation, actually. But yeah, are there any questions about B plus trees, or B trees, or external data structures? Okay, if there are any, just drop them in general. And if I have got anything wrong, I'm terribly sorry. Just correct me here, or in general, just so everyone has the correctest information. Later on, so yeah, no, that's everything. Okay, let me